Welcome students. Design of machine elements 1 we will be covering. So we have VTU syllabus of 18 ME 52. Okay, and under which I will be covering the module 5, that is part of module 5, that is power screws. Okay. Coming to the efficiency of the square thread screw, so it is the ratio of torque required to raise the load without friction to the torque required with the friction, nothing but T dash divided by T. So sigma is equal to T dash by T, where T dash is equal to WD by 2 into tan alpha, or efficiency we can rewrite it as tan alpha divided by tan pi plus 2, which you can get it in the design data handbook 9.11F, or else if the collar friction is added, then that part also will be added, which you can get it in the 9.12B equation in your design data handbook. Now we'll look into the self-locking and overhauling in the power screw. So we know that in the screw jack, if you rotate it for some height with the load, it will be retained at the same height. So you can see here it will not come back to the original position by rotating by itself, even in the presence of the load. So such type of locking in the power screw, wherever it is placed, even during the load, it is the phenomenon, or its property, I can say, is called a self-locking condition. So if the opposite thing happens, that is nothing but overhauling in the power screw. So it is nothing but self-locking, locking at the same position, and if not, it will become a overhauling in power screw. So we know that torque required to raise the load is given by T is equal to W by 2 into D2 tan pi plus alpha. Suppose in this equation, if you can see pi is less than alpha angle, then what happens is T will be negative. It indicates that load will start moving downwards without the application of any torque. Okay, such condition is known as the overhauling of the screw, or back driving of the screw, even without application of any force or a torque. This will find an application in Yankee screwdriver. Okay, so therefore we can rewrite this equation for the overhauling condition, where tan alpha is greater than FD2 plus FCDC divided by D2 minus F into FC DC, in case if you are considering the collar friction. Okay, so suppose the second case, if the pi is less than greater than or equal to alpha, then T will be positive, right? So it indicates that load or effort is required to lower the load, and in such condition it is known as self-locking screw. So this will find an application in screw jack. Okay, so you can see here tan alpha is less than tan pi, then tan pi is less than f, because tan pi is f. So we can rewrite tan alpha is less than f d2 plus fc dc divided by d2 minus f into fc dc. More, one more method in which the efficiency has been explained. We know that efficiency is equal to tan alpha divided by tan pi plus alpha. So self-locking condition, as I said, is the pi angle is greater than or equal to alpha. So if that be the case, so what happens is efficiency is less than tan pi divided by tan 2 pi. Okay. So suppose pi is equal to alpha. So or else efficiency is equal to or less than tan pi into 1 minus tan square pi divided by 2 times the tan pi. Or else you can rewrite this equation, n is less than or equal to half minus tan square pi divided by 2. Thus, efficiency of self-locking screw is less than or equal to 50%. On other hand, if the efficiency is more than 50%, then the screw is said to be overhauling. Now we will discuss about the bearing pressure that usually happens in the power screws. So in order to reduce the wear of the screw and the nut, bearing pressure on the thread surfaces must be within the limits. It can be limited by providing good lubricant condition and rubbing velocity. So assume a uniform load distribution. The bearing pressure equation is given by length of the nut Ln is given by number of threads into pitch, nothing but N into P. So you can rewrite Ln is equal to N into P is equal to 4 times the W divided by PB. PB is nothing but a bearing pressure into pi into D to the power 2 minus D1 square. Okay, where D1 is the core diameter D1. Okay, so coming to the V thread or angular thread power screws. Okay, so instead of you have seen the square thread. Okay, there are V thread screws are there that we have discussed. For V thread, included angle is 2 beta, which is 29 degrees in Acme thread and 30 degrees in isometric thread. That is nothing but a thread angle. Okay, so from the figure cos beta is equal to W divided by Fn, or Fn is equal to W divided by cos beta. But frictional force we know, right? Frictional force F is equal to F into Fn is nothing but F W divided by cos beta, nothing but F into W secant beta. Okay, so effect of the thread angle is to increase the frictional force by the term secant beta. To account for this effect, frictional coefficient F is replaced by F secant beta. Hence, in all the equations of V thread, we change the equation wherever it is with the T is equal to W by 2 into D2 tan alpha plus F secant beta divided by 1 minus F tan alpha secant beta plus FC DC. So that is what we can see from these equations. So wherever the term associated with the V thread, we will be replacing that with the F secant beta. Okay, so this is used in the equations. So look at the problem. So a square threaded power screw has a nominal diameter of 30 mm and a pitch of 6 mm with double threads. A load on the screw is 6 kilonewtons and the mean diameter of the thread collar is 40 mm. The coefficient of friction for the screw is 0.1 and for the collar is 0.09. Determine the torque required to raise the screw against the load. Second, the torque required to lower the screw in the load. Third, overall efficiency. Fourth, is this screw is self-locking. So we need to check that. Coming to the data of this problem, nominal diameter is nothing but D is equal to 30 mm, pitch D is equal to 6 mm, double thread is equal to N is equal to 2, load W is equal to 6000 newtons, mean diameter of the collar is DC is 40 mm, and the screw coefficient of friction is 0.1, collar friction F of C is equal to 0.09. Now look at the mean or pitch diameter equation. D2 is equal to D minus B by 2, nothing but 30 minus 6 by 2, nothing but 27 millimeters. Lead angle tan alpha is equal to L by pi D2 is equal to 0.1415. Now look at the equation for the torque required to raise the screw against the load. So where you have TR is equal to W by 2 D2 into F plus tan alpha divided by 1 minus F into tan alpha plus FC DC. So this equation you can get it in your data handbook with equation number 9.12a in our Balvi textbook. I mean the design data handbook. And if you substitute all the values accordingly, then you get 30,642.27 Newton meter. Now coming to the torque required to lower the screw against the load given by TL is equal to W by 2 D2 into F minus tan alpha divided by 1 plus F tan alpha plus FCDC. So if you substitute all the values of W is equal to 6000, F is equal to 0.1, D2 is equal to 27 and tan alpha is equal to 0.1415, FC is equal to 0.09, DC is equal to 40, then you get an answer 7485.40 Newton meter of torque required to lower the screw, okay, against the load. Now coming to the overall efficiency if you substitute again in the value of equation of efficiency, so you substitute all the values, it comes out to be 37.40 percentage of efficiency it shows. Coming to the is the screw is self-locking, that is the fourth one we need to find out. So there are two ways in which we can find the self-locking checking. That is one thing, if the efficiency is less than 50%, usually the screw is self-locking, or else we use equations to find out it. So we know the condition for self-locking, that is tan alpha should be less than F D2 plus FCDC divided by D2 minus F into FCDC. So this is the equation to be used for this problem. So if we know the value of tan alpha is equal to 0.1415, and if you substitute all the other values, then we will find 0.1415 is obviously less than the right side. Okay, it comes out to be 0.234. It shows that a screw is self-locking.